Your discovery has meant that this chronic and disabling condition now can be permanently cured by antibiotics.
Hi there, I'm Professor Barry Marshall at the University of Western Australia. I've got a talk here called Nobel Journey, Man versus Helicobacter, and it's a personal story of my discovery of Helicobacter pylori with Dr. Warren and how we went on to win the Nobel Prize. And you know, a lot of this research was done in Western Australia, and we pretty much consolidated it here at the University of Western Australia in the first few years before everyone in the world heard about it.
Your pioneering work has also stimulated research all around the world to better understand the link between chronic infections and diseases.
It's all right doing research, which you would say, discovering something. Then you want to use that research for something useful, innovate, make a new product, a gadget or something. And then finally, you want to translate it, which means roll it out to the public, make it a benefit for everyone that you know or in the whole world in our case. So that's what wins the Nobel Prize, as far as I can tell. They like to see that it actually translated into something very useful that everyone wants to know about and take advantage of. Even when I was in high school, I liked science, and I came second in a science competition in 1967 when I built a refrigerator. And my father's a refrigeration engineer, so that was pretty easy for me to do. But I did have to learn all about thermodynamics, why refrigerators work, latent heat, entropy, all that stuff, which if you do physics, you've heard of that. Anyway, the judges were coming around to look at all the projects. In the evening, it was very, very hot, no air conditioning, but I had used my refrigerator to freeze some icy poles, and so I was able to give these icy poles to the judges. And so they liked that. This is like I had the knowledge, I'd innovated, created something and translated it into useful activities such as feeding icy poles to the judges. The innovation and the translation is something that I was also always good at, and I suppose it's just my background was like that. So let's get back to our discovery, which was for the cause of peptic ulcers. And here you've got a duodenal ulcer on the left and you've got a gastric ulcer on the right. Remember, this duodenal ulcer has eroded into a blood vessel. The patient just about, bled out with a vomiting up about a litre of blood. And on the right is a gastric ulcer. Now that hasn't gone all the way through the stomach wall, but remember the stomach wall's about 8 millimetres thick. And I guarantee this ulcer's gone through 4.5 to 5 millimetres. So there's not much left to go. And certainly a perforated gastric ulcer used to be a fatal condition before we had emergency surgery and everything. But people with ulcers, it was a serious condition and they would be a bit worried about going on a holiday to a remote city or a funny island or something, because they could at any stage have a major complication from their ulcer. And so it was a potentially fatal condition which affected about 5% of the population who are walking around for most of their lives with this risk, this little cloud hanging over their health. Now, pre-Helicobacter, people knew that bacteria were killed by acid and there was a lot of acid in the stomach. So they're like, you can't possibly have bacteria living in the stomach. They're killed by acid. And also they did experiments on experimental animals, like they would stress some mice and rats and things like that, and show that sometimes these animals did develop just ulcers like that. So the idea that emotional stress could lead to ulcers seemed to be a pretty good explanation, because stress would cause high acid levels and then ulcers. So acid and stress were really thought to be the cause of ulcers. There was not really any good data on it. So one of the things I learned was whenever something's potentially caused by stress, you should say to the doctor, okay, but what's the real cause? Because there probably is a real cause. We're all under stress, and it's really a bit of a cop-out for the medical practitioner to blame everything on stress just because they don't know the cause of it. So be aware of that. Be a bit suspicious and ask for the evidence. And these days in medicine, we always like to talk about evidence-based medicine. So you want to see, what data was there that showed that this disease was caused in this way, or this treatment works or doesn't work. Remember, there's no point looking for bacteria in the stomach if all bacteria are killed by acid. However, if there was a bacteria that could survive in acid, that would probably be a problem, and that's Helicobacter pylori. So here's Helicobacter pylori. It just means that it's helical. So it's got 1.5 twists. So any kind of spiral bacteria, we usually describe it by its thickness, and it has flagella at one end, which helps us swim in the mucus layer of the stomach. And most of the bacteria that inhabit that part of the gut, just along the lining, are twisty, spiral, and motile. The word pylori is a Greek word meaning gatekeeper, so that it was found at the bottom end of the stomach where the muscle is called the pylorus, which holds the food in the stomach. So that's Helicobacter pylori. It's easy to remember. You can always call it the helicopter bacteria. I don't really care about that. So a very interesting and handsome-looking bacteria, if I may say so myself. Now, Dr. Warren, he's a pathologist, and so he was always getting biopsies of the stomach sent to him just to see if there's any cancer, because cancer of the stomach used to be a lot more common. And one day he said, what's this smudgy blue line? And he put a special stain on it called a silver stain and stained bacteria black. And my God, he says, there's enormous numbers of bacteria here sticking to the wall of the stomach. You can see the roundish yellow blobs, they are cells, and then around the edges of them you'll see these many, many curved bacteria sticking around the edges of the cells. Now the thing about Warren, he's not just satisfied, that's contamination or something else. He's there like, hang on a minute, these bacteria are all identical. And he knew that if you took samples of bacteria from the mouth, you'd find rods, cocci, fungi, lots of different, purple ones, pink ones. You wouldn't find a homogeneous colonization like this. So he knew that this meant these bacteria were actually living in the stomach, so they must be resistant to acid in some way. So the curiosity-driven research that Warren and I started off doing was, wow, how could these bacteria live in the stomach? There's so much acid. Must be something new. So we didn't set out to find the cause of ulcers. We just were curious about something, a new bacteria, and wow, it's resistant to acid. That's pretty interesting. So we did a study where we did 100 patients and 58% or 58 had the bacteria. So these were people with all different kinds of stomach problems, not necessarily ulcers. But very interestingly, if a patient had a duodenal ulcer, all 13 of those patients had the bacteria in the stomach. There's 100%. It's like going to the casino and on the roulette wheel getting red 13 times in a row. You can see that would be pretty unusual. There's something going on there. So that was an association. And also gastric ulcers, we saw that about 80% of gastric, which is the stomach ulcer that I showed you before, those ones were 80% infected with the Helicobacter. So this was pretty amazing. And we didn't really know whether it was just in Western Australia, in Perth, or whether it was all over the world. And so the question was, would the world accept the new cause for ulcers on the basis of data from only 13 patients? No way. And so this started a journey. You think, how come nobody believes me? But the scientific process is that all your mates and everybody else who's in science, when they see a new discovery like this, they try to prove that it's wrong. And they say, we don't believe it. We're going to try and prove that it's wrong. And after a year or two, they say, we can't prove that it's wrong, it's probably right. So that's the scientific process we like to go through. And when you go into university and you start doing your own experiments, you should be prepared to try and prove yourself wrong whenever you've got a discovery like that. And then you'll be confident you've already tested and you're not worried about other people not believing you anymore. However, don't assume that any new discovery is immediately going to be accepted. And Dr. Warren and I submitted our paper to the meeting of the Australian College of Gastroenterologists in 1983. And they sent me back this letter. Dr. Marshall, I regret your research paper was not accepted for presentation. The number of abstracts continues to increase. We had 67, we could only accept 56. And so, Dr. Marshall, your paper was rejected in the bottom 20%. Actually, it was one of the worst ones, they reckon. And they said, you can't even have a poster. In fact, we don't want you to come to the conference. It's a bit embarrassing to see this kind of stuff presented there. And so we were very, very sad. But luckily, we did have some friends overseas and we submitted it to an international meeting 6 months later and they thought it was great. And so we were vindicated to some extent. But always keep your rejection letters. And many years later, you can show it in your lecture, as I have done. It's you get a lot of satisfaction out of that. So why is there so much resistance to new ideas in medicine and science? And the person who really figured this out was a person called Dan Boorstin, who used to be the librarian at the US Congress. And he said the greatest obstacle to knowledge is not ignorance, it's the illusion of knowledge. And so if you've discovered something, a new technique or the answer to a difficult problem, there might already be a lot of people out there who are using some other solution, some other strategy, and they say, well, we don't need any new things. We've already solved this problem. And you say, well, in actual fact, your solution costs $10,000 and mine costs $100. So that sounds like mine's better, doesn't it? And they say, oh, no. You can see there could be whole industries around a paradigm which everybody believes in. So you come up with something new. They say, we don't need anything new. We've already got the answer. So that's the illusion of knowledge, and that's where we were. Everybody thought stress was the issue. Acid caused ulcers. So the treatment was antacids and drugs which lowered the acid level. And that was a $3 billion business. So certainly they weren't going to suddenly close up shop and start using antibiotics just because of 13 patients in Western Australia. So how do you go to prove that a new bacterium is harmful? And the answer is you test it out on small animals. You do it on rats and mice and guinea pigs, and ultimately we even tested it on pigs. But these bacteria, human bacteria, they didn't necessarily infect animals. So, didn't really work. The person who described this originally was Robert Koch in 1882. And he had the same situation as we had. He tested a lot of people to see if they had these funny bacterium in their sputum. Like if they had a bronchitis or cough or something, you'd say, look at a sample, and look at the sample, you see the TB bacteria. And everybody said it's so common, and many people who aren't really very unwell have this. So how could you say that that's a fatal bacteria that causes fatal tuberculosis? So what he did, he infected it into guinea pigs. And sure enough, they got tuberculosis and died, and he could sample the TB bacterium. So he says, you infect an experimental animal, and then if TB develops, it's proven the bacteria are harmful. And he called this rule Koch's postulates. So we had to do that on animals, which didn't work. So finally, in my lab, I brewed up some Helicobacter and drank it down one day in 1984. And I thought that probably nothing would happen because people with ulcers didn't really remember catching the bacteria. So I thought that initially it wouldn't make you sick or anything. Just a few years later, you might get an ulcer. But big surprise for me, I did feel quite unwell and had vomiting for several days in the week after I took the bacteria. So that was interesting for me, but I still wasn't convinced that it was the bacteria. I thought, it could be just psychosomatic or something, and I was feeling a bit tired. But after a week or so, Dr. Warren and colleagues did an endoscopy on me, and the stomach looked a little bit red, and then looked under the microscope at the biopsy sample from the lining of my stomach, and it was exactly like we were seeing in the ulcer patients. Many of these bacteria were growing in my stomach, and there's a lot of inflammation, which means white cells were there coming to eat the bacteria. So that's the underlying abnormality then, which causes ulcers. And so people were saying, oh no, the ulcer comes first, and the bacteria were just harmless, just sitting on top of it. But we showed that a person without an ulcer, a perfectly healthy person, could be infected with these bacteria and therefore potentially go on and cause ulcers. So that was the beginning of a big saga. We did lots of other experiments, and one of these was to answer this question: how else could you prove this new bacterium is harmful, especially to cause ulcers? Well, one day we decided we're going to eradicate the bacteria with antibiotics, and we'll see if they got their ulcers permanently cured and didn't have to take medicine anymore for the rest of their life. And so we did that experiment, and we did a double-blind, placebo-controlled randomized study. That means we chose by a sort of a lucky dip which treatment patients were on. And some of them got real antibiotics, some of them got fake antibiotics with different treatments. And the patients had no way of telling which treatment they were on. So they all thought they were on the real treatment, but of course, half of them were on fake antibiotics. And we wanted to see whether they were cured or not if they got the real antibiotics. And so it has to be prospective and randomized and placebo-controlled. Now, remember those words, because quite often you'll see advertising in the health magazines about some new kind of treatment, like cleansing diet, etc. And that would not be prospective, randomized, and placebo-controlled. And the reason these things are so important is if you've got a new treatment, a new drug or something, you really have to prove to the government that it works using this method. And if you prove that it works, then the government has to pay for it. So that's the great thing for the pharmaceutical industry. They're always trying to get over these milestones and get new drugs on the market that have been totally proven. So that's the process that goes on with every new drug, and that's why it takes a few years before you actually see it in the pharmacy. So let's go back to our curiosity-driven research here. How can a bacteria survive in the human stomach and resist the acid? So that was an interesting scientific question that we still hadn't answered. And we found out that Helicobacter makes this enzyme urease, which splits urea. Now, urea, you may know, is just a waste product, comes out in your urine, but it consists of CO2 and ammonia bound up together, and you would pass that out harmlessly. And you see on the left-hand side, that reaction consumes a hydrogen ion, which you see as H+. That is acid. So the acid gets soaked up in this reaction. And on the other side of the equation, you've got the ammonium and carbon dioxide. And so Helicobacter is able to protect itself from acid by making an alkali to surround itself with a little bubble. And so unlike nearly every other bacteria known to man, Helicobacter can survive in the acid. It has no competition. Once it's down there, it's locked in there for life, and you really can't get rid of it until you take antibiotics. On the x-axis, you'll see that's pH. Acid is on the left and alkali is on the right. And then those three lines are different bacteria. And you see some weak urease producers, and one of them is Proteus, and I think that's the dotted line at the top. And you'll see that below, as you move from the right to left, you see below 3.0, all those bacteria are killed. Whereas if you look at the thick black line, that's Helicobacter, and you see you put that into an acid solution with some urea, and it's making the ammonia to protect itself from acid. And as you go to the left, it gets right up to pH 1.5, which is extremely acidic. And Helicobacter is still alive after 35 minutes. So just remember, it's much better at producing this enzyme and making ammonia than nearly every other bacteria known. I show this because it just goes to show how clinical medicine has connected now with chemistry. And so we were doing chemistry, playing around with some bacteria, and that really translated then into a discovery which affected millions and millions of people with ulcers around the world. So don't be ashamed of doing some kind of weird little experiment if it's interesting to you. Just follow your instinct. And I always say if it's curious and interesting and you like to do it, there's probably some value in it. So I mentioned that the translation of this discovery was to use the urease to pick up H. pylori. So one of the things we started doing then was making a gel which gave a pH change and went red when ammonia was present. So we're taking samples from patients, putting them in these little gels, and that's a CLO test. And the one in the middle is a positive one. You see he's gone pink after about 10 minutes. The gastroenterologist would just put the biopsy in it, put it in his pocket, and then within 10 minutes, look at it, say to the patient, you've got that bacteria of Dr. Marshall's, and take some antibiotics and you'll be cured. And on the right there, I've just got a culture of Helicobacter on a Petri dish, blood agar. And the reason you do that is because then the microbiologist can test different antibiotics, and we can make a recommendation to the patient as which antibiotics to use. And that's called personalized and precision medicine. So in 21st century, we don't just take an average and have a bit of a guess what the average person needs. quite often we'll do something very careful and find very, very detailed information. Even a bacterial genome these days is possible to do in a few hours, and we'll see which is the best antibiotic. And so the cure rate goes up, probably more than 90% just in a couple of weeks, and the side effects from the antibiotics goes down. So the future is very bright with this kind of precision medicine and personalized medicine that you'll be able to get from every doctor in the near future. Now, the other thing is, once you've had the bacteria treated, how do you find out that it's gone? Well, you don't want to have another endoscopy. You can do a breath test. And typically we give an isotope labeled tablet with urea in it, and you'll see it sits in the gastric mucus layer, and the starch bead will actually go down to where the cells are, and the bacteria are all living down there on the cells. So the urea gets pushed down into the mucus layer, touches the bacteria, and then gets split into the CO2 and the ammonia. The ammonia goes into the stomach, and the CO2 immediately enters the bloodstream. And on the next slide, you can see what happens to it. So within one circulation time, you see the CO2 is going up to the lungs and being breathed out. You catch it in a balloon, and the tiny amount of radioactive tracer, it's equal to background in 24 hours just from the environment. So it's so tiny, we don't worry about any risk. And it goes in, we look at it in a scintillation counter, which is kind of a Geiger counter. So here we've got physics rolled into chemistry, into a clinical problem to diagnose patients. And I'm very proud to say I invented that so many years ago. And now we reckon that about 30 million of these tests are done around the world every year, probably more than that. One of the issues is that H. pylori is becoming resistant to antibiotics, and you like to culture it to see what antibiotics will kill it. Endoscopy and biopsy costs, probably $1,000. And then how else could you get a sample of the bacteria without actually doing an expensive procedure, in the outback? And we did a research study in Jigalong, which is an Indigenous Australian community with very little health care available at the site, thousands of miles from Perth. And we used a string test. So in this test, you've got a string wrapped up inside a capsule. You swallow the capsule, and then you wait an hour, and the bacteria will stick to the end of the string. And so then we can get a sample of bacteria. And we did this on the nurses at the hospital. We found out quite a few nurses in their careers had picked up Helicobacter just from nursing patients with ulcers. And so that was a benefit for everybody, really. So his string should be about 1 meter long. And then after about an hour and 90 minutes, we just pull the string straight out, and we cut the end off and culture that to find those bacteria and work out which is the best antibiotics to treat. And we can also do studies on the genome of the bacteria because we're able to culture it now non-invasively. So we've developed that string test further, and we're helping a company develop it for China, and probably it'll become very, very popular because you don't have to be the owner of $1 million lab to culture Helicobacter pylori and make the diagnosis with the string test. So after 100 years, after he started the Nobel Prizes, actually, we find out that Alfred Nobel probably had Helicobacter. It was very, very common in the 19th century. Nearly everybody would have had it in Europe. In his biography, it says that he always complained of indigestion, and he was simply overworked or under serious mental stress, no matter which restaurant or hotel he was staying at. It was probably, the Ritz-Carlton or the best possible one. He was always complaining about the food. So he was a very cranky old fellow. And of course, he's always on an ulcer-type diet. But in those days, you couldn't diagnose ulcers unless the patient died and you did a post-mortem, or perhaps they vomited up some blood. So it was a bad problem. And if only he had got someone to make this discovery when he was still alive, he might have been a lot better off. I'll finish off by saying that the future of the human race, as far as I'm concerned, and most Nobel laureates will tell you this, is technology is going to continue to advance, make life easier for us and far more predictable. And since 50 years ago when man walked on the moon, lifespan has increased by 10 years. And every 6 years that we go further, we get another year of lifespan. So most Nobel laureates will live a long time. And I project that at the moment, my lifespan's looking like 106, but could even be more. Thank you for your time today, listening to my Study Australia virtual masterclass. I'm Professor Barry Marshall, Nobel Prize winner. in Perth, Western Australia.